Hello everyone, my name is Rabia Asghar. I'm a PhD student at UGA in RIA, and I'm going to present our paper, Flow-Guided Motion Prediction with Semantics and Dynamic Occupancy Grid Maps. Motion prediction in autonomous driving remains an open and a challenging problem. This challenge arises from the inherent uncertainty in the sensor data, a complex behavior of agents in the scene, and the fact that even with the complete knowledge of the environments and the agent's behavior, there are multiple possible future outcomes for any given state. Now, in a typical autonomous vehicle stack, we collect onboard sensor data to perceive the surrounding environment and predict motion of dynamic agents in it. Most approaches in the motion prediction assume the detection and the traffic of agents within the scene are pre-processed. This reliance introduces limitations such as confidence thresholding during detection and tracking, and some end-to-end learning approaches bypass these limitations by directly using sensor data, but then they usually work with fixed sensor setups. In our work, we leverage a dynamic occupancy grid map that directly processes the sensor data to represent the scene. OGMs provide a simplified bird's eye view grid with occupancy information. They offer flexibility across sensor modalities and efficient sensor fusion, real-time computation, and a dense probabilistic occupancy representation allowing for modeling sensor and prediction uncertainties. For our input, we consider a sequence of OGMs with semantic labels. Our proposed framework predicts the current semantic grid of the scene and collectively sequence of both the future semantic grids and the future flows. Additionally, we iteratively warp the current semantic grid with the future flows to obtain a sequence of warped future semantic grids. The novelty of our work lies in a multitask framework that combines OGM with semantic labels to predict multi-step vehicle semantic grids as well as multi-step flow of the entire scene. We evaluate our approach on a real-world NuScenes dataset and show that the prediction of warped semantic grids improve the understanding of the environment, prediction capabilities, and network's ability to recognize vehicle behaviors within the scene without prior maps. Now let's discuss the scene representation in our work. We use a Bayesian dynamic occupancy grid filter that generates grids from LiDAR sensor data. In the images here, we show camera images for visualization. Now, each cell in the state grid that you see on the right contains probability estimates for 4 possible occupancy states. This can be unknown occupancy state, illustrated in red, or dynamic or static occupancy state, illustrated in green and blue, or free occupancy state, shown in black. In this example here, we show a dynamic bus on the top and a lot of parked vehicles in the rear on the grid. Additionally, this framework provides velocity estimates for each cell represented by a mixture of grids and particle sets. For semantic information, we represent it in a form of a semantic grid that contains the probability assigned to each cell for being occupied by a specific semantic category, and in this case, vehicles. For this, we consider camera image input and repurpose the lift splat shoot architecture. The original LSS architecture extracts feature maps from multiple input camera images in bird's eye view and decodes them into vehicle occupancy prediction represented as the semantic grid. Our adaptation involves concatenating corresponding OGMs alongside the feature map and decoding the combined information into this semantic grid. This fusion results in a more comprehensive understanding of the scene. Altogether, we represent our scene with OGMs and the semantic grid for our input. Moving on to the decoder end of our multitask framework. So our network is equipped with two decoder heads. One is dedicated to predicting the current time step semantic grid, while the other forecasts sequential future grids and flows simultaneously. The flow is represented as a two-channel grid that models the velocity of vehicles along x and y dimensions. Now let's consider a simple case where we have semantic grid on the left and the flow at the next time step. We use backward flow to capture vehicle motion from their future positions back to their current position. So at each time step, the backward flow contains velocity vectors for each cell, indicating the change in occupancy from the previous time step. The warping operation is performed between the current semantic grid and the future flow grid at the next time step. For the pair here, we learn warped semantic grid as the one shown on the right. And we show the vehicles that are displaced because of the flow in purple. Worth noting in this approach is that our method not only predicts the flow of the occupancy, but also incorporates potential flow in the free space. This warped semantic grid is then further warped with the next flow, and this process is repeated iteratively for all the subsequent time steps to yield a sequence of warped vehicle semantic grid. Moving on to our prediction network that takes inspiration from video prediction approaches. Each frame in the input sequence is passed through the spatial encoder. The generated features are sequentially fed into the convolution LSTM block that enables simultaneous capture of spatial and temporal information. To allow for multimodal predictions, we adopt the conditional variational approach. This approach allows the network to learn two distributions that capture the evolution of the scene in latent space. We have a present distribution that is conditioned on the present spatiotemporal features, and a future distribution that is conditioned on both the present features as well as the future ground truth. Finally, the spatial GRUs use the spatiotemporal features to iteratively forecast future states conditioned on the sample from the Gaussian distributions. All vehicle semantic grids in our network are trained with binary cross entropy loss, which is a classification loss. The flow grid for the flow grid, we defined an L1 loss only for the cells that are occupied by the vehicles. And additionally, we introduced the KL divergence loss to encourage alignment between the present and the future distributions. We evaluate our proposed model on real-world NuScenes dataset. For the training set, we use 23,000 sequence and we evaluate on 5,000 test sequence. The input consists of LiDAR-based DOGMs and camera image-based semantic grids covering an area of 60 by 60 meter. Each sequence is 3.5 seconds long, with the input comprising of 3 frames representing 1 second, and the output consisting of a present frame and 4 future frames representing 2 seconds. The 4 future frames include predictions for both the semantic grid and the velocity and the flow grid or the flow grid. For qualitative results, we present scenes involving both static and dynamic vehicles with diverse behaviors. On the left, we show a sequence of dynamic occupancy grid map with semantic labels, illustrated with white cells over the state grid. In this first example, there is traffic in opposing direction and a bus is entering the scene from the left. On the right, we display the ground truth and predictions for the flow and the warped semantic grid. The flow is shown on the top, while the semantic grid is color-coded from black to purple to indicate different time steps. Now, in this example, you can see on the top the ground truth flow shows only the vehicle predictions, but our network predicts the flow for the whole scene. In our predictions, we see these trails of blue and red capturing direction of traffic flow without the map information. And the segments that are occupied by static occupancy in the state grid, that was the information coming from our input, our network learns no flow. You see those as the white regions in the predicted flow grid. This feature actually helps learn safe prediction of dynamic agents in the scene. For example, here for this bus, with the help of the flow, the predictions are quite cautious, avoiding the areas with static occupancies in the scene. In the second scene, we have dense dynamic vehicles. We see that the warped grid maintains a safe distance from the nearby dynamic vehicles, especially towards the top of the scene. Again, something that's helped by the flow predictions. Similarly, in another scene, we see vehicles turning to the right in the bottom. And our flow warped grid are successful in avoiding collision to static obstacles in the scene. We conducted an evaluation study to investigate the role of semantic flow using different configurations of input and output. In terms of the metrics, including intersection over union and area under the curve of the precision recall curve, we note that the IOUs of our proposed network is quite comparable to other methods. But it's mainly the area under the curve that improves with using flow prediction. This indicates better precision and recall of the predictions that are made with the help of the flow. Furthermore, we evaluate the network's ability to predict both static and dynamic agents by tracking individual agents in the ground truth. Unlike classic video prediction approaches where the vehicles become blurry or disappear when the network is uncertain, our method is able to better retain both static and dynamic vehicles in the scene. In conclusion, we present a novel forecasting approach that leverages dynamic occupancy grid maps and semantic information to predict scene evolution as flow-guided semantic grids. Our framework is capable of multimodal predictions, learning patterns, and behaviors based on the observable static scene and motion of the dynamic agents. By predicting flow alongside the semantic grid, this method tends to improve prediction results, especially in the dynamic parts. For future work, we plan to extend this framework to include the prediction of additional semantic classes as well as unidentified grid-level components by learning the flow of the entire scene. Thank you very much for your attention. Please feel free to send any questions or comments to my email. Thank you.